Let's go ahead and get the recording going, and let's start talking about circuits. And the main thing you guys want to know to understand for circuits is Kirchhoff's two circuit laws. What are the two Kirchhoff's laws for circuits? One of you give me one of them.
Isn't it like one is the voltage rule?
Mm-hmm. So
The other one.
So what is the voltage rule?
Was it like something like the same amount of voltage that goes out of the battery is the same amount that goes in, something like that? I forgot the exact wording of it. Hold on. Something like that.
Yeah, I'm looking for a little more than that.
Yeah. I'm not going in depth. I don't remember the exact wording, but where are the slides? Okay.
I think the one you were trying to talk about there would be the conversation of electric currents. That's the one with the in and out.
Mm. Yeah. So there is a voltage law that we need to understand.
That should be also called a loop rule on that one.
Exactly. So what is it?
It's the sum of the voltage around the loop. And all that sum of the voltage equals 0.
Is that for what sort of loop?
That doesn't really say what type of loop it is, but
So would it be
the only thing is only for conservation electric fields. That's the only thing I'm on the slide on it. Honestly, it's the only thing I'm getting from that. That the loop.
I would think more of it doesn't specify what kind of loop. So that means it should work for literally any loop in a circuit. So basically Kirchhoff's loop law, so the first one, loop. So we have the sum of the voltage is going to be 0. And that's for literally any loop inside a circuit. Anywhere where you can, sort of like draw a, connecting circular path around, starting at one point in the circuit and ending back at that point, the total voltage along that closed path is going to be 0. So, for example, let me go ahead and do this. This loop law applies for this loop around here. It also applies for this loop around here. It also applies for this loop around here. It applies for this loop around here. And
if that's closed.
Yeah, if the switch is closed, obviously, if it's included in the circuit. It applies for literally any loop in a circuit. The total voltage gained and lost throughout that loop is going to be 0. So what if so what happens to the voltage when you go across a battery if we're going this way? Are we gaining voltage, losing voltage?
That should be gaining.
Exactly. We're gonna gain some sort of voltage. I have a number for the problem, 10 volts, but it doesn't matter. And then when we go across a resistor, what happens to the voltage?
Depends on the direction, but it does depend on the direction of the current.
Mm-hmm. So we're going down this way right now.
All right. If the current is going the same direction, it will be negative IR.
Mm-hmm. Exactly. And what law is that?
Circuit conventions.
Specifically the IR.
Oh, specifically the IR.
Mm-hmm.
What was that name again?
V equals IR.
Oh, Ohm's law.
Exactly, Ohm's law. And that's the other main law you guys need to know. You need to know Kirchhoff's two laws, and you need to know Ohm's law. And with that, you can pretty much solve any problem you'll see on your quiz tomorrow. So Ohm's law, V is equal to IR. That's the voltage dissipated across a resistor. Or we can also use it to calculate the current through through a battery in a circuit, if we find the total net resistance of the circuit. So if we're losing voltage going across a resistor, why is this loop, if we're going to start here, go around like this? Why is this loop total zero if there's no battery, so we're not gaining any voltage, but we're going across two resistors? How is this loop zero?
Well, the only thing is, one's going one direction, the other one's going the opposite. So I would think, like, it would be a negative IR plus a positive IR. It would just cancel each other out.
So what direction is the current traveling for both of these? What direction is the current traveling through this resistor? Up or down?
Down.
Down. What about the current through this resistor?
Up.
Is it up?
Well, that's what you drew pointing up.
Well,
but...
this is the path we're taking for our loop. It doesn't have anything to do with the direction of the current.
Oh, the current. Okay, so they're both down.
Exactly. They're both down. So essentially, if our path that we're drawing for our loop is going with the current through a battery, we're losing voltage. But if we're going against the current, it's as if we're like gaining the voltage back. It's like
And then which will just once we return to the original point, it will be both ways we went would be the exact same voltage, just one's a negative direction, the other one would be a positive.
Exactly. Boom. So now, what's Kirchhoff's other law?
The current rule?
Yep. So what is his current rule?
That was the one that you were saying. In equals I out. The sum of the electric currents going in equals to the sum of the electric currents going out.
For what?
Conservations? It's the junction rule.
Junctions. So any junction in a circuit, for example, right here, or right here, or right here. So for a loop, we have total voltage is zero. For a junction, we have the current in equals current out, or the total net current is zero, I guess, if you're saying the total current in is equal to zero, or you know what I mean. So essentially, junction sum of I in is equal to the sum of I out. So literally just these three laws here, and then there is one other thing you need to know that has to do with the power dissipated across a resistor. Does anyone know what's the power dissipated across a resistor?
Oh, dissipated? Ooh.
So for example, if the resistor were a light bulb.
Oh, is this just the P is equal to IV, which is also equal to I square R?
Mm-hmm. And then there's,
Okay.
Yep, and then there's a third way you can write it. It's not actually on the equation sheet.
Eh, uh, that's not it. That's our stuff.
There's a third way you can write this in terms of V and R.
Oh, there it. Well, I don't actually remember if you went over that at all.
Well, think of it. How could we solve for IV in terms of V and R?
Uh,
How do we find I in
so
terms of V and R?
would that be V squared over R?
Yep, exactly.
Okay, then.
We use Ohm's law. I is equal to V over R, and we plug it in. So V squared over R. You don't really need to you don't really need to know that. As long as understand these two, you're fine. And I think that's why he's omitted this from the equation sheet, because it's just one more thing to confuse people. But it's still useful to understand how you can actually get that. So, I'm sure you guys have figured out at this point, circuits are sort of a bit annoying in terms of actually, breaking down the circuits and understanding each individual part and solving for the currents and the voltages.
That one
and
question on discussion, yeah, that.
If you want, we can go over it near the end. But so, literally, just the best way to understand circuit stuff is to just practice. Do practice problems, work through them, and practice breaking them down step by step. So let's go ahead and hop into an example. And if you want, we can look at that discussion one at the end, because it really doesn't matter what examples we go over as long as we're going over examples. So we're going to have 3 resistors here, and they're connected as so, and they're connected to a 10-volt battery. And we have the resistances 100 ohms, 300 ohms, and 250 ohms. The battery has an internal resistance of 10 ohms. Actually, have you guys gone over internal resistance yet? I think that's next class, actually.
Internal resistance of a battery?
Yes.
We went over briefly last lecture, but not for a lot much. They said that the most of the time it will be we won't have to deal with that, but there will be maybe one question in the future, very few, there might be some in the future, but most of the time we won't have to deal with it.
Yeah, I remember him. I do remember him talking about a resistance. Yeah.
Yeah, so because basically there's no such thing as a perfectly resistanceless battery, and there's no such thing as a resistanceless anything. So, but in this case, let's ignore the internal resistance. We're just going to say it's negligible. So, has 0 internal resistance, and we're going to have the switch initially closed. So, with the switch initially closed, what's going to be the current through the battery, and then also what's the current through each resistor, and the voltage drop across each resistor. Let's take 10 minutes, then we'll go over it. We want the current through the battery, the current through each resistor, voltage across each resistor.
Yeah, there was this one homework problem I just did not know, so let me slide in here.
Yeah, I mean, so we'll go over this example, and then we can probably look at some homework problems or some discussion stuff. Because honestly, the best way to work out this stuff is to just practice and get comfortable with it. So anyway, you guys have had about 10 minutes to work through it. So how do we go ahead and find the current through our battery here? How do we find the total current through the battery?
The total current throughout the battery.
put all the resistors together.
So how do we put all the resistors together?
Well, I started by adding the R1 and R2 together since they're right next to each other in parallel.
So we have R12. How do we get R12?
Or multiplying R1 and R2 and adding them and then dividing that.
So R1 times R2.
R2 divided by R1 plus R2.
Yep. By the way, if anyone's wondering, this is exactly the same as doing the 1 over R12 is equal to 1 over R1 plus 1 over R2.
This is basically how the formula of series will be, but it's in the opposite.
Yeah.
Because this one's parallel.
Yep. So
I always write it that way, the R1 times R2, because it's just simpler for me.
I do too. Yeah. When I first discovered this, I was like, this is so nice.
Yeah, I tried to do it the other way, and I'm just like, I kept making mistakes, and I was like, yeah, no, okay, do it this way.
Mm-hmm.
Less chances of mistakes.
And so that's how you get R12. And then is R3 being included in the circuit right now?
Not yet.
Is it included in the circuit?
I actually think it is, because didn't you say that the switch was initially closed?
Exactly. Switch is initially closed, which means it is connected here.
Yeah.
So
that means we need to do that parallel with R1 with R12 with R3.
Yep, exactly.
So okay. It's just another multiplication thing.
Yep. And then how do we get the current through the battery?
Well, that will be the voltage of the battery versus all the resistance, the R123.
So you're saying the voltage times the resistance, or
sorry, over divided
by yeah. I think you cut out when you said over.
Okay.
Yeah. So the total current, we'll call it I naught, current through the battery, is equal to V naught divided by R123. And we can go ahead and calculate values. I'm going to do the 1 over rule because I think it's easier for doing 3 resistors at once, because all 3 of these resistors are parallel to one another. So it's 1 over 100. It's what, 100, 300, 250. Yep. Plus 1 over 300 plus 1 over 250 by our -1. That is our total net resistance. And then we have our 10 volt battery. 10 volts divided by the total net resistance. We get a total current of about 173 milliamps, or 0.173 amps. That's pretty simple. It's just breaking down the entire circuit and using Ohm's law. Does anyone have any questions?
So how do we, what's the difference? I know when it's closed, everything's connected, and then when it's open, like, stuff isn't connected. But where would the voltage like still go through? Would it still go through R1 and R2, but not R3, or is it just like a different way?
So if the switch is open?
Yeah, if the switch is open.
So if the switch is open, essentially this part of the circuit just gets cut off. So it's like as if it doesn't exist.
Okay.
Like,
yeah, that's what I thought.
Yeah. So just treat it as if this part of the circuit is just invisible. Block it out.
Okay.
Ah, crap, I can't do that. Oh, crap, I've seriously messed up. I can't undo that many things. All right, this is...
You can't?
This just lives here now.
Oh, no.
I guess you can only undo the last, like, 5 or 6 actions you've done.
Can you not erase it?
I could, but I could just be like, all right, we're going to erase it little bit by bit.
Oh.
Whatever. I know what I can do, actually. I can do this. and we've just beheaded the A, and then I can just repaste it in from earlier.
Oh, okay, thanks.
Okay. So now, how do we find the current and the voltage across each resistor?
The current between each resistor.
I'll give you a hint. I think it's easier to find the voltage first.
Well, yeah. Since they're parallel to almost throughout, wouldn't the voltages be the same?
And what voltage would that be?
10.
Exactly. All of them have a voltage of 10 volts. So C is 10 volts all. Because all of the resistors are parallel to one another, and there's no other resistor in the circuit. So Kirchhoff's loop law, any loop voltage is 0. We gain 10 volts here, and we lose 10 volts across each of the individual resistors. And so then how do we find the current through each resistor?
You can say, go ahead.
I is equal to volt over R
Exactly.
for each one.
It's just Ohm's law. I is equal to V over R. So V over R. So we'll say I1 is 10 volts divided by R1, which is 100 ohms. So it's 100 milliamps. I2, we're dividing by 300. So 10 divided by 300. 1 over 30 is like, I think, 0.3.
0.3. 0.3,
Yeah.
I think. Be,
So about 33 milliamps. And then I3, 10 over 250. It's about 40 milliamps.
So wait, amps to milliamps is like it's 100 difference?
It's 1,000. So 1, 2, 3. So we moved the decimal point 3 places.
Oh, okay then.
Yeah, I prefer writing, for these currents, I prefer writing milliamps because it's nicer to write like 40 or 100 or 33 rather than 0.04 amps or 0.033 amps. Just personal preference, but you could keep it in SI units. So now, if each resistor was a light bulb, which one of these resistors would be the brightest?
Since we know the currents to each one.
Would it be, no. Wait, it's based off of current, isn't it? So would it be R1? R1?
It's not just based off current, but you're not wrong. It is R1.
Is that and voltage?
Mm-hmm.
Okay.
So how do you get which one is brightest? It's the power dissipated, right?
Yeah.
What's the power dissipated, Zama?
It's equal to V times I, so voltage times current.
Mm-hmm. And so R1 has the highest current.
Yeah.
And they all have the same voltage drop. So
I gotta remember that.
R1 is the brightest.
Yeah.
Pretty simple. So, anyone have any questions about this so far?
Wait, hold on. So, so R1's the brightest because it's closest.
Because
no, it's because no, it's the current. The current is stronger at R1. Because we're going by, in order to figure out which one's brighter, we base it off the power, which is P is equal to I times V. The voltage is the same throughout, but each one has a different current. And the current in R1 is stronger than the current in R2 and R3, which will cause the brightness to happen more. The light bulb will be brighter.
Because of the power.
Exactly.
Yes.
Could literally,
okay.
I literally could not have said it better myself.
I at least understand the power, the rules of power at the very least.
So you better not lose any damn points in your quiz tomorrow because of it.
I hope not.
So let's go ahead and now we're going to go ahead and open the switch. So what changes when we open the switch?
Well, there's definitely not going to be a current in R3.
So does that mean we could literally just do this? Goodbye.
I believe so. I don't think any flow or current will go through R3.
Exactly. So let's not calculate the values again because that's pretty simple. What is going to happen to the current through R1 and R2? Is the current through R1 and R2 going to increase, decrease, or stay the same?
I think in this case it will stay the same.
Why is that?
Well, there's no other resistors. There's no other things happening. The only thing that's different is the current is just not going to flow to R3, but it's not going to change the flow of how it goes to R1 and R2 to the battery.
But would the current through the battery change?
I think it would.
Yeah. Do you know is the current through the battery going to increase or decrease?
I think it would increase.
Why is that?
Because there's less resistance.
There is indeed one less resistor.
Yes.
I must warn you guys. What have I mean, Roger, you'll especially know this. Shanazoma, you haven't come to all the sessions. What's the one thing I've been saying about physics in general this entire semester?
Why is everything topsy-turvy?
Nothing makes sense. Nothing makes conceptual sense. Yes, what you guys are saying does make sense. Oh, there's one less resistor. That means there's going to be less total resistance, which means there's going to be more current.
That's not...
No.
I think it would decrease, and I don't know why, but I feel like it's because it's parallel.
Yes. So essentially what happens here is when you're connecting resistors in parallel, you're actually decreasing the total resistance of the entire circuit. If that makes sense. Which it doesn't. And so what Roger said earlier with the currents through each individual resistor, they are actually the exact same as if R3 was here or not. Because how do we find the current through each resistor?
I equals a velocity over R. And it's just
velocity.
I'm looking at something else. Voltage over R.
Let me see. What is this? 121?
Hey, I just saw magnetism. We kind of need to know a little bit of velocity on that one.
That's true. You guys will get to that next week, I believe, right? Or is it late this week? I think it's the end of this week.
Really next class.
Yeah. So it's V over R. Is the voltage... What's the voltage through each of these resistors when R3 is disconnected?
It's still going to be the same.
It's still going to be the exact same. It's the same voltage, the same resistance. So the current through each of these is the same. But the total current through the battery is going to decrease because there's less total current in the entire circuit. We disconnect this resistor, which means there's less current in the entire circuit. So less current through the battery.
I don't understand.
Yeah. I'll be honest. Don't try to memorize this or be like, oh, we disconnect resistors and the current goes down and whatnot. I recommend calculate R123 or R12 or whatnot every single time and double check and make sure.
By doing the calculations, I could see, it's definitely decreasing.
Exactly.
1, 2, 3, because 10 divided by 50.
Yeah, like we calculated it earlier. R123 was about 57 point nice ohms. And then R12 would just be about 75 ohms. So it's actually a greater resistance than R123. Something to think about.
Yeah.
So,
it actually decreases by 4.
Mm-hmm.
Like 0.4.
Yep. So that's fun, right?
0.04. Okay, there we go.
Mm-hmm. So, if R3 is disconnected, which is going to be brighter out of R1 and R2?
It would still be R1 because again, the current on R1 and the current R2 still stays the same, and it's still the same velocity. Okay. Again, magnetism. So those numbers won't change. That means the powers won't change. That means R1 will still produce the more power.
Exactly.
So R1 will still be brighter.
Yep, exactly. And that's the thing, like, we literally disconnect R3, and R1 and R2 don't change at all. Nothing happens. They don't get brighter, they don't get dimmer. Absolutely nothing happens. Which is interesting. So theoretically, you could just connect an infinite number of... You could theoretically connect an infinite number of light bulbs in parallel to one another, connected to just one battery, right? And just have infinite power output.
Until the battery runs out.
Yep, and until eventually you're going to end up frying the battery because you'll have a gajillion amps going through it. But yeah, I mean, theoretically, if you had a super battery that would never fry, you could do that.
Till the light bulbs go boom.
Yeah. So that's pretty much it. I mean, I have this example here where I just have, a few batteries and a few resistors in this circuit. But if you guys want, we can pull up some other examples. So do you guys want to go over this example here? I mean, just practicing breaking it down, or do you want to go over some of your discussion and homework?
To be honest, the thing right here is almost the same, around the same as discussion. So
I was going to. The thing is that you haven't talked about Kirchhoff's rule yet, and I would like if we went through that one problem on the homework where it had, I think it was 2 batteries and 6 resistors, and I was like, "What is going on?"
Here, take a picture of it and put it in session text, and we can take a look at it. Yeah.
I drew it out, but I already closed my laptop for flippage physics.
Hang on, so it's on Kirchhoff's law. I got to flip it right here, so I can just easily. Oh, do you know the name? Actually, hang on, maybe I already found it.
It's the one with 2 batteries and 6 resistors. That's the name of it. I remember.
Okay, I think I found it.
Sounds like a fun problem.
It's not fun.
Is it the optional one?
Is it called the 3 loops?
It's with 3 loops, and it shows R1 to R6. There's V1, V2, and they give the current directions for I1, I2, and I3.
Okay. Okay, so R1, I1, I2, I3. Does it also have like an I5? See, this is what I mean. I'm trying to figure out which one.
It's on the second homework we have to do. It's for Kirchhoff's rule, but it's like the second to last problem.
I'd say if it looks annoying, that's probably it, and just post it in session text.
Oh, okay, here we go.
And even if it's not the exact problem, it's still good to go over it.
I I don't know how to go. Like, I think the most I could do sometimes is like 3 loops with maybe 1 battery. But once it's like
let's
2
see if
batteries and 3 loops, I just don't know.
All right. Oh boy.
Is this it?
Yeah.
Okay.
All right. So
When you said second to last, then I was like, okay, because there were a few of them that had multiple Lars and loops and all that.
So a circuit is constructed with 6 resistors and 2 batteries as shown and has no actual usable purpose in real life. Why is this thing on Flip It? Whatever. The battery voltages are V1, V2. The positive terminals are indicated with a plus sign. Okay. The values for the resistors. Why does it give these stupid values? Why can't it just give like 50 and 100 and
That's what I was saying. When I
stuff that
saw the
rounds
values,
nicely?
I was like, what?
Yeah, it just makes it so you
Why
look
not just
actually...
ones and twos? Something
Yeah.
very small.
Yeah. All right. The positive directions to the currents I1, I2, and I3 are indicated by the direction of the arrows. And so I'm assuming it wants you to solve for I1, I2, and I3.
Not just they told us to solve for V4 was the first one, but my thing is I wanted to know how to form the equations for this type of like for these batteries and loops.
Mm-hmm.
I wanted to know if
V4
there was
caused
just like
the R4.
Yeah.
yeah.
Here, give me just a moment.
I'm not sure if we're supposed to put like I know there's for current. There's like
Oh God.
it depends on nodes or something. I'm confused.
So
I'm
let's...
just not sure about the number of equations we have to write.
Yeah. So there's... Let's do this, and I'll zoom back in. There we go. So there's two. So what are Kirchhoff's 2 laws? Uzoma, it's Roger, Sean. We went over it at the beginning.
The 2 laws is the current law.
The
You
current
want me
law.
to actually say it? Which is the sum of the currents in equaling to sums of the current out.
Mm-hmm.
And then the voltage rule is the sum of all the voltages equaling 0.
For what?
For any closed loop.
Exactly. So let's start with the current law. There's one equation we can write down for our current law here. Let's say for this junction right here. What's the total current in?
Total current in?
I2 is going, looks like it's going.
Mm-hmm. And what's the total current coming out?
I1 and I3.
Yep.
Oh, wow.
I2 is equal to I1 plus I3. Boom. That's one equation we can write down. So,
okay.
So it's specifically asking us to solve for I1, I2, I3. I mean...
It does ask for that, yes, but it also is asking for the voltage on R4.
Okay, so for that we'd need I4 as well. And which I'm going to take an educated guess. And I'm going to say it's traveling this direction. We can make up the direction and it doesn't matter. Why does it not matter?
Because if it's, what did they say? If it's like, if the answer comes out negative, it's not wrong. It just shows it's in the opposite direction.
Exactly. So essentially
It basically just changed the direction and you'll be fine.
Yep. And then we'll also have I6 here.
Is there like is there an I5 or is that all just I4?
We'll just call it all I4 because it would be the exact same current going through R4 and R5.
That was my problem. That was also another thing. I was like, it's all in the same loop, so it has to have the same current.
Yeah. So essentially,
Okay.
we have 5 unknowns, which means we need to have 5 equations in order to solve for everything. And it's going to take a stupid amount of algebra, but don't worry, there's a way to simplify it. So
Please tell me.
Yeah, I guess seriously, that's when it gets nuts.
It's using our little friend called linear algebra and matrices.
Okay.
So let's...
Matrix. Oh boy.
Yeah, it's honestly, it's actually really simple, and you guys have access to your computers during your quizzes. Just go to Symbol Lab, and you don't even have to solve it yourself.
Okay.
But
so didn't say it using online calculators, so I guess
we still need 4 more equations. What's another equation? Let's say let's do this loop here.
Cool.
so we gotta get an equation for almost any all the loops. Okay.
So we'll go through here. So it's minus I1 R1.
Yeah.
Because we're going with it, and I'm not going to write I1 R1. I'm going to write minus. I'm going to write the actual value for R1. So minus 71 I1.
Okay.
Okay.
And then we go
goes
up.
to the battery.
So it's plus V1, and once again I'm going to actually write the value plus 18.
Mm-hmm.
And then we're going against I3 through R3, so it's
minus.
It's minus negative, so it's plus. And then
see, that's what's confusing me too. If it's going against the current, it's positive.
Yes.
Yeah.
Okay. All right.
So minus 71 I1 plus 18 plus 100 I3 is equal to 0. So that's our entire loop.
Where does that equal to 0 come from again?
That's just the loop law. Yep.
Okay then.
Total equals 0. Let's draw another loop. What's another loop we want to do?
I'm guessing the I2 loop.
Do you want to go in here?
Yeah.
Sure thing. So let's start at B here. So we're gonna go and we're gonna go up. So we'll go plus V2, which is 12 volts. So plus 12, and then we're minus R2 I2. So minus 148 I2 minus 100 I3, and then we go through V1, but we're going against it, so it's minus 18 volts, and then we're going with our defined direction, so it's minus R6, so 148 I6 equals 0. That's an ugly loop.
Very.
So now we have 3 equations. We need 2 more.
So how do you know how many equations for the voltage rule? Like how many equations we would have? Is it based off the loops?
Well, so I am actually saying we need 5 equations because we have 5 unknowns. However many, like throwback to high school and like algebra, however many unknowns you have, you need that many equations in order to simplify and solve.
Oh, that makes sense. Okay.
So let's keep with the current track record. Let's go around this loop here. So once again, it's going to be plus 12 volts minus. I'm going to combine R4 and I5, R4 and R5 here. How do you combine resistors in series with one another?
Working, just getting that money.
In series, you just add them together.
Exactly. So 124 plus 71, 195 minus 195 I4.
Wait, what was it? 124 plus 71.
Yeah.
Yeah, that's right.
Is equal to 0.
And for V2, wait, are we? It's positive because I'm trying to see what direction we're going in. It's clockwise?
For this one here, we are going clockwise, but for some of the other ones, we went counterclockwise. It really doesn't matter.
Yeah, I know these two are counterclockwise, but this is clockwise.
Yeah, it doesn't. We could write the exact equation counterclockwise or clockwise. It's just add negative signs.
Yeah, so, and if it has a negative sign, just put a positive sign on it.
Yep.
That really is it.
So we need one more equation here in order to actually solve this. I say let's go ahead and let's use the junction law one more time. Let's say A.
A?
Okay.
What's the total current going in?
It's just I3 goes in there.
I3.
And I1.
And what goes out?
I6.
Exactly, I6. Or in this case, I'm going to go ahead and write it as I2 is equal to I6, because I2 is equal to I1 plus I3 as well. Right?
That does make sense, yeah.
Wait, could you explain how it equals to I2 again?
Because we got from earlier, from this junction, I2 in is equal to I1 plus I3 out. And for this one, it's I1 plus I3 in is equal to I6 out. So that just means I6 is equal to I2.
Basically, the current from I2 is split up into I1 and I3, and when they meet up again, once they hit the point A, it just comes back the same.
So now we want to.
I was trying to ask, will we have another equation for what is it, for the junction at B, basically?
We could, but we haven't actually defined a current going through V2. Which, I mean, we could if we wanted to, but it's like, whatever.
There looks like there is no need for it.
Yeah, there's no need for it. We have 5 equations. So now what we do is, for each equation, we essentially would rewrite it so that we have any constants on the right side. So for this equation, we'd move the 18 over, so it'd be negative 18. And then, like, for this equation, it would be 18, so we have is equal to positive 6 over here. And this disappears. And this is negative 12. And for these ones, it'd be, we'd, like, move I6 over, so it'd be 0. So it'd be, like, I1 plus I2, I1 plus I3 minus I2 is equal to 0. And so for each of these columns, we essentially write down all the values. So for example, for this one, for this equation here, we have minus 71 I1. We have no I2s, so we'll write that as 0. We have plus 100 I3. We have no I4s. We have no I6s, and it's negative 18 at the end.
Oh,
on the other side.
Wow.
And then we'll do the same thing for these other ones. For this first one, we have plus I1 minus I2 plus I3 is equal to 0, because we could we could move this over. And then we also have plus I1 plus I3 minus I6 is equal to 0. And we have 0 I1 minus 148 I2 minus 100 I3, no I4s, minus 148 I6 is equal to 6. And then for the last one, 0, 0, 0, and it's negative 195 I4 is equal to negative 12. And so then we're essentially just going to hit go, and what we want to do is reduce this into its row reduced echelon form. If you haven't taken linear algebra, you really don't need to understand it. Literally all you need to know,
I've never taken that before.
Yeah, literally you just let Symbol Lab do its thing and reduce it down to this 1 0 0 0 0 and a bunch of ones, and you have the values here.
Mm-hmm.
These values are your currents.
Well,
So for I1, it's going to give us these ugly fractions, but we can just like plug them into a calculator and solve. Exactly. So from this, we should get I1 is equal to. I'm gonna pull out my phone's calculator because it's easier than switching tabs constantly. So it's going to be about 113 milliamps, or 0.113 amps. I2 is 28858. It's going to be about 13.4 milliamps. I3 is about 100. It's actually negative 100, or 99.7. I'll keep 3 sig figs. It's in the negative. It's negative, so that means that we actually had our direction wrong, and our I3 is actually upward. The problem was wrong. Heaven forbid. So, I4.
I mean, again, fix that with just putting in a positive.
Exactly. I4 is about 61.5.
And then with that I4, you can solve for V4.
Exactly. Yeah. And then I6 is 387 divided by 28858, about 13.4. It's the exact same as I2.
Oh yeah, because you said they were equal.
Yep. So boom, there's all our currents. Symbolab did it for us in 5 minutes. I mean, literally all you have to do is write down the equations, punch them into the Symbolab matrix solver, and boom, you have all your current values.
And I had another question on that, because I noticed that there is like 5 spaces down and to the right. So is that equal to the number of unknowns that we put the matrix in, or is it the number of equations?
Yeah. So the number of rows. So this is a 5x6, right?
Yeah, it's a 5x6. The number of rows indicates the number of equations.
Yeah. The number of rows is the number of equations, and then you just have one more column than the number of rows, and that's for your, like...
Yeah, you want the one more column because you do have constants equaling to that. So, like, that one equation that equals to 0, you want to include that.
Yes, exactly.
Could y'all repeat the columns? I get the rows one, I just don't understand the column.
You just... So it's 5 rows for 5 equations, and then you just add 1, so you'll have 6 columns.
And the reason behind it is because...
The last column is the right side of each equation. So each equation we're rewriting so that all the constants are on the right side.
Oh.
So for example, for this equation, it's negative 71I1, so we put negative 71, plus 100 I3, and we don't have any I2, I4, or I6. It's all 0. And all of that is equal to negative 18. So we put that in the last column.
Oh, it's the equals.
Yep.
Yes.
And for example, for this last one, it's negative 195 I4 is equal to negative 12. So 0, 0, 0, negative 195, 0, negative 12.
Gotcha.
I would not think linear algebra will make this type of equations simplified.
Like, I've got to be honest. I don't know what the hell Flip It is on, but does it really expect you to solve this with 5 equations and doing all the algebra? And
yes, that's exactly what they want us to do.
I'm gonna go throw up, honestly. Like disgusting.
So okay, with this is actually a cheat sheet for this type of thing, basically.
Yes, it's magical.
I'm so happy.
I really want to know the actual explanation how this works with that, but at the same time, it probably is too convoluted.
They wanted us to do the algebra for it, so I was
Yeah.
gonna struggle with that. But now that I know that there is Symbolab, I will use that.
Symbolab Matrix Solver. It's magical.
Hey,
Yep.
the Symbolab was helping me for Calc 3 for a lot of things. So trust me, if you go with higher difficulties of math, you may want Symbolab to help you with that.
I'll be honest. I got through. I literally have a degree in physics because of Symbolab and integralcalculator.net. So.
Yeah.
If I can do it, you too. It's magic. All right. Well, hopefully this helped out. Definitely. If you guys have any more questions about using Symbolab as a cheat sheet for solving all the systems of equations, remember it's not like really a cheat. You still have to set up the system of equations.
Yeah.
It's not. Yeah, you still have to get the equations correct and everything. So it's not really cheating or nothing. And plus, on the syllabus on the thing, nothing says that you can't use an online calculator.
Exactly.
Calculators are allowed, so.
Exactly. So if you guys have any more questions about using Symbolab, feel free to ask me later on in the day. I can answer questions. I have to go prep for my 121 session, which I'm supposed to host in 10 minutes. So thanks, thanks guys for coming. Hopefully this helped out. Praise be to praise be to Symbolab. And good luck studying for your quiz tomorrow.
All right, thank you.
All right, bye guys.
Thanks.